Hey guys, today we've got lesson 7.5, which is solving rational equations. Also, sorry I said hey guys, because some of you might be gals or not guys, so hey y'all, how you doing? Let's go. If you don't know, y'all is one of the best words we have in the English language. My mom's from the South, so I was raised on y'all, and it makes communication so much easier, right? Like one time, I had a friend say, "Are you guys going to go to your guys' house?" Okay, think about that. Are you guys going to go to your guys' house? Talking to like a family of siblings. And then my cousin from the South came over one time and she said, "Are y'all going to y'all's?" And it was like, oh my gosh, that's so much better. Are y'all going to y'all's? So if you don't use the word y'all and you're saying stuff like you guys, just get better. Just say y'all. Because now, even if you're not from the South, you can start using that word. It's not cultural appropriation. Maybe it is, but the fact is it's just a good word. Start using it, okay, y'all? Okay, if you skipped the first 2 minutes of this video, that was probably wise of you. We've talked about simplifying rational expressions, where we'd factor and do things and find common denominators and cancel common factors when possible. We're now going to take expressions and set them equal to each other, make equations, and solve them. So here's one we kind of started the year with. Problems like this, where we have a whole bunch of fractions. Remember, every number is a fraction. So that 5, I'm going to think of as being the fraction 5 over 1. The lowest common denominator of the numbers 1, 3, 4, and 7 is actually all those numbers multiplied together, which is 84, right? 3 times 4 times 7. So I'm going to get a common denominator for each of these fractions. On the left, this needs a 28. And if you're not sure how I knew it needed a 28, I thought of it this way. I thought, I need to get 3, 4, and 7. This has a 3. It needs 4 and 7. Well, 4 and 7 is 28. So this number has a 4. It needs 3 and 7. So I'm going to multiply that by 21 over 21. And this trick I'm showing with basically using the prime factors is going to be really useful in other cases also. The 5 obviously needs just a 28 on top and bottom. No, sorry, a 84 on top and bottom. And this needs a 12. Because 3 and 4 make 12. Now, I don't have to do any of the arithmetic on the bottom. I know it's going to be 84 everywhere. It's the top I have to worry about. 2 times 28 is 56. 21 times x is 21x. 5 times 84 is 420. 2x times 12 is 24x. Now that I've got a common denominator, the magic happens. I can multiply everything by 84. I can do the same thing to both sides of the equation, multiply by 84, and all these 84s divide to 1. So I've taken a fraction problem, and I've killed the fractions. Now solving from here should be pretty trivial, right? We're going to combine like terms, like get the variables on the same side, so add 24x to both sides, subtract 56 from both sides, and we get that 45x equals 364. Divide both sides by 45, and x equals whatever this is. I don't think that can reduce. It definitely can't reduce. This is a 45, not a 75. There's our solution. If you want to find the decimal, go for it. If you want to check the decimal, take that answer, plug it into x, and plug it into x, and see if it works. Okay, so we started the year with problems like that. It's a good reminder, because that process of getting a common denominator and then canceling all the denominators through multiplication is going to be how we solve all of these. Okay, so here's one that looks more like our more recent types of problems. And again, the key to this is common denominators. It'll also be domain restrictions. So remember how I said that the name of this chapter is factor and do things? Well, I need to factor this. But most of these problems factor really easily. In fact, frequently, they tell you how it factors to begin with. It turns out that this is just x plus 3 times x plus 5. So I factored. And the lowest common denominator, well, I need to have at least 1x plus 3. I have to have exactly 1x plus 3 and exactly 1x plus 5. So my LCD is x plus 3 times x plus 5. Well, that means I can just do some giving of what's needed to both sides here and start solving. This needs an x plus 5 on top and bottom, because now I have x plus 3, x plus 5. And this needs an x plus 3 on top and bottom. And this doesn't need anything. This is already okay. So I do some multiplication. I have 2x plus 10 over x plus 5, x plus 3, minus 3x plus 9 over x plus 5, x plus 3, equals 1 over x plus 5, x plus 3. Now I'm going to multiply both sides entirely by the LCD of x plus 5 times x plus 3. And that causes all of these to cancel. And I've again killed my fractions. So what I'm left with is 2x plus 10. Let me change back to my green. 2x plus 10 minus 3x minus 9. Remember to distribute that negative. Minus 3x minus 9 equals 1. And I just solve this. 2x minus 3x is negative x. 10 minus 9 is 1. It's positive 1. And this equals to 1. I subtract a 1 from both sides. And I get that negative x equals 0, which means that x equals 0. Well, that's kind of crazy. I didn't actually, no, I made this problem up, so I don't know what it was going to work out to. I thought it was going to be something kind of messy. It turns out it's just x equals 0. Is that really possible? Is 2/3 minus 3/5 equal to 1/15? Right, I plugged in a 0 for x to get 2/3, plugged in 0 for x to get 3/5, plugged in 0 for both these x's to get 3 times 5 is 15. So I have 10/15 minus 9/15 equals 1/15. Yes, it checks. Wow, that's crazy. I think I'm kind of a genius that I can just make up random problems and they come out nice and pretty. It helps that I'm using 2s and 3s and 5s because those add up to each other. So maybe I'm just, formulaic. We got the solution x equals 0 and we checked it. You have to check it. There's the very real possibility that you get an answer that doesn't actually work, even though it looks like it does. For example, suppose this had come out to the answer x equals negative 5. It didn't, but suppose it did. Well, x can't be negative 5, because if you look up here, if you plug in negative 5 for x, you'd be dividing by 0. And we can't be dividing by 0 because that's undefined. So we actually knew from the start that there's two things we couldn't have. We couldn't have negative 3 and we couldn't have negative 5. So if we got a negative 3 or negative 5, it would have been no solutions. And that's why these domain restrictions we practiced before are so important. They let us know what x can and can't be, and sometimes that becomes a problem. We'll see that here. This is a problem I pulled out of your book. It's 8x over x plus 1 equals 4 minus 8 over x plus 1. Again, I'm going to worry about common denominators and about domain restrictions. So think of this as the fraction 4 over 1. And that 4 over 1 needs to have its x plus 1 attached to it. So I'm going to multiply the top and the bottom of this by x plus 1. That gets me a common denominator. I'm going to have 8x over x plus 1 equals 4x plus 4 over x plus 1 minus 8 over x plus 1. And now I know x cannot be negative 1. Because if x was negative 1, that would cause us to divide by 0. And dividing by 0 is a problem. So I'm not going to be, if I get a solution that's negative 1, I'm going to say this equation cannot be solved. And we'll see if that happens. I think it does here, but we'll see. Now that I've got a common denominator everywhere, I can multiply both sides by x plus 1. And that gets me a bunch of death. 8x equals 4x plus 4 minus 8. Combine these like terms. 8x equals 4x minus 4. Subtract the 4x from both sides. 4x equals negative 4. Divide both sides by 4. Ha, there it is. X equals negative 1. But x can't equal negative 1. We know that if x equals negative 1, then this has division by 0, and that has undefined no solutions. So this has no solutions. This is a set that cannot be solved because we got a solution that can't work. That's called an extraneous solution. An extraneous solution is a solution that cannot work when you check it. So with these homework problems, you have to check every single one every single time. Okay, that's all for today. See you next time. Y'all have a good day.